Hi, and welcome to a Hopper 6502 video. 6502 being the 8-bit microprocessor from the late 70s. Hopper is a modern semicolon and curly brace language, similar to C or C# or Java, but with, garbage collection. So it manages memory for you. It's similarly structured to Pascal in that it has units, so it doesn't have classes. Hopper is both a language and a development environment, and all the tools you see in this video are all written in Hopper too. So everything except for the Windows runtime that I'm running on, which is the virtual machine that I run on Windows, is all written in Hopper. The other runtimes are mostly now written in Hopper as well, and then translated into C, or we'll see. So what's this video about? I'm going to have a series about the recent work I've been doing on the 8-bit microprocessors, both the 6502 and the Z80. So let's go see what that's about. So I've been trying to find ways of making it easy to work on these retro platforms with a way that where the hardware is available to other people without having to buy historic machines or have hinky things. And these guys here, these RetroShields, RetroShield adapters, they were originally made for the Arduino Mega. So and that's how I first tried it with the Mega, which is this guy here with the Z80 on it. So this is a Mega compatible board from an Arduino Mega, compatible from DF Robot, and that's the Z80 on it. And in the background, what I have running in the background here is a Teensy now. So instead of the Z80, I've got a Teensy. So let's go have a look at where these RetroShields come from. So the advantage of the Teensy is it runs at 600 megahertz, which is significantly faster than the Mega. Yeah, I think the Mega runs at like 16 or something. So what he did, I mean, he's been making these boards for a while, and so what he recently did is he made an adapter for Teensys. There's the Teensy microcontroller. It's the first time I've actually used one of these microcontrollers. And by making this adapter, which is a Mega, footprint, it meant that all his existing boards for all the different microprocessors that he supports would still work on that same form factor. So he wouldn't have to rebuild his boards. He just supply a Teensy adapter. Anyway, so that's the first part, is the hardware. And so it's not the cheapest way to get up and running on a Z80, but I think when we go penny pinching for something which we spend a lot of time and energy on, it's not worth it. It's worth ordering this kind of stuff, and often your shipping is going to cost more than the device anyway, and you're only going to buy it once, and you're going to spend a lot of time and get a lot of joy out of it. And what these do is they use the microcontroller to simulate RAM and ROM and peripherals, so that all you've really got in your RetroShield, where's the 6502 one? Do I see it here? There it is. All you've got on the RetroShield is the 6502 itself. So it's got very few chips on it. It's got some, capacitors and resistors and some jumpers and things. Like these resistors here, but it's mostly just the 6502. All right. And I've been working on the RP2040 board for a while now. The Raspberry Pi Pico compatible microcontrollers. So I've been wanting to get back to the 8-bit platforms for a while. And in moving to the 8-bit platforms, I've done a lot of work on the Hopper runtime since I was last on the 8-bit platforms about a year ago. So I wanted to rewrite the runtime, and the runtime for 6502 is written I hand coded that in assembler, and it's like 20,000 lines of assembler. It's quite tedious to work on. So, and to to run Hopper, if this is like a Hopper program here. So if I build this and I've got that board connected, and then if I hit F5 to run it, it'll upload it into the debugger. There we go, successfully uploaded Fibonacci into the debugger. And now if I step through it, F11 to start single stepping, you can see me stepping into the recursive calls here, and you can see my watch window on the right with my stack and my variables, and I hit F5 here. Fibonacci, it took 10 seconds to run because I was in the debugger, and 55. So if I control F5, it'll run it without stopping. There we go. And we can use F9 to set breakpoints and all the stuff you expect to see in a debugger. And in addition to that, if I Alt F4 out of this and go to the console, this is the Hopper console. There's the Hopper monitor as well. So the Hopper monitor is, I use this a lot for debugging, but it's more, so what we saw in the debugger was Hopper source level debugging. And if I load the Fibonacci sequence up here, just for clarity, this is running on the 6502 right now, not on my Windows machine. So what I'm seeing here is the 6502 machine. So what the monitor is it's Hopper bytecode level debugging. So you still see the Hopper source code in green here, but the bytecodes here are in purple. And so you can, single step through the bytecodes here, and you can look. Let's do a few more. Again, you can show the value stack. So that's the current virtual machine value stack. You can show the call stack. You can set breakpoints, all the usual stuff. So there's two debuggers that I've been always making them work on all the different platforms that I've been supporting. The one is the bytecode level debugger, which is very useful for debugging the system itself. And the other one's the source level debugger, which I expect will be what most people use. So I make the same debugger protocol work on all the different platforms that I'm supporting, so that I only have one set of tools to work against. And because I first started on the 6502, they all assume this zero memory page from the 6502 zero page. And based on the zero page, let's do C for zero page, it'll show you where the PC is, the program counter, the base pointer, the stack pointer, the heap, all that stuff. And I think if we go zero page here, I think I've got a Google Sheet. Let's have a look at that. Switch to my desktop again. So I map it out. I've changed it over time, but I map out how I use the zero page on the 6502. So I mostly use the top two lines here. So you can see that's where the program counter is. And if you look down here, if 5D program counter, so 5D00. And what else can we see in there? In the middle, we can see the heap again, 900 and heap size over here. So at the top here. Anyway, so even though the protocol is the same for all, irrespective of which platform I'm running on, it's all based on the architecture of the original 6502 version. And it doesn't really matter if I'm running on an RP2040 or not. That still applies. Anyway, this rambling video is turning to sort of an overview of what I've been working on. So the key here is I recently wrote a new runtime for the 6502. And it's the way you get it there is you're running on a Teensy, and I'm using the Arduino IDE. So in the Arduino IDE, I've got a program that I derived from the work that was done by the 8-bit force guy, Erturk. And I've made it support my serial port so that I can communicate with it. And basically it provides the RAM and the ROM for the microcontroller. And this is the, in one CPU tick, it simulates a clock as well. It can read RAM, it can read ROM, and I've got a ticks thing for doing real-time clock as well. And then the guts of it is in this ROM image here. So it's just the image of the ROM that was in 6502 code, and it sees this and runs the program in the ROM. So how do you how do you make this ROM image, right? How do you build your 6502, written in 6502 assembler, a Hopper runtime? And that's what this is about. So let's go have a look how I did that. So I've got another shortcut here to go and have a look at that. So that changed to a different path. So now this is the Hopper runtime that I've recently been working on. It's not complete, it's sort of minimal. So yeah, we can go have a look at that again. If I look at Fibonacci, I'm building for a minimal system. So right now I don't have all the features of Hopper. I'm sort of building it up again from the ground. I'm sort of bootstrapping it. And so it's missing a few of the, it doesn't have dictionaries or lists here, for example, or even arrays. No packed instructions, minimal runtime. Packed instructions is a way of getting the code density much higher with having a bigger instruction set. So if I have if I don't have packed instructions in the Hopper virtual machine code instructions, I can build a much smaller virtual machine and get it all working. And then later I can switch on packed instructions and the optimizer will make these programs a lot smaller. It is one of the big advantages of Hopper bytecode running on small machines, is that the code density of the Hopper bytecode is much more dense than even the native code for that machine, which means you can get bigger programs running on there because the opcodes do a lot more than an actual native opcode would do. Anyway, let's go look at the runtime I've been working on. So this is the crux of this video. Let me get rid of the display. So I've been working on this in the Hopper environment, of course. So the Hopper preprocessor preprocesses this file. But this is not Hopper. This is assembler, 6502 assembler. So if I press F7 to build here, if we look at the bottom of the screen, assembling, optimizing, and generating code for 6502. So I've written a 6502 assembler in Hopper and optimizer. And the structure is very familiar to people who are familiar with semicolon and curly brace languages. So usually an assembler, for example, the comment is done with a semicolon. And usually an assembler, the way you do a hex digit is with a $sign. So and usually an assembler, these parentheses would mean an indexed or indirect, an indexed entry. Whereas for the semicolon and curly brace programmer, that means an expression. Whereas to index in C or C# or Java, you use these the square brackets. So my syntax it's very comfortable if you're switching a lot between the two environments, which I am. So I'm switching a lot between programming in Hopper and programming in assembler. And another interesting thing you'll notice about this assembler is it has things you don't normally see in assembler, like a switch statement, or a loop, or an if statement, and even methods. So, and it has all the useful, the usual Hopper navigation, like I can right click on that and it'll take me to it, or I can right click on that and it'll take me to it, and then I can go back through those. Anyway, so let's go have a look at that one. Is available. So it has what look like methods, but they don't have return values and they don't have arguments, because that doesn't really make as much sense in assembler. Because you can put, return values and arguments are sort of however you want them to be, whether they're on the stack, whether they're in registers or not. Anyhow, and yeah, constants and constant expressions. So if I right click on that, I can define constants the same way I would in Hopper, that are very familiar with you. And it has units as well. So I can, I'm in the unit for serial, and I can go from there to the actual device driver unit like that. So it has units, it has a program, it's very much structured like Hopper. And in fact, it's using the same preprocessor as Hopper, just with different keywords being legal. So let's go and look at is available again. And behind the scenes, it's doing a lot of the grunt work for you. So like an if statement with a branch like that, an if statement isn't really branching on the 0 flag. Well, it is branching on the 0 flag, but it's not coming in here based on the 0 flag. It's it's doing the opposite. It's skipping when it's not 0. It's jumping past when it's not 0, and it's doing nothing when it is 0. It's just continuing the normal program thread. So behind the scenes, this flips the condition to NZ and flips the jump to be to the end. And it actually uses 2 jumps in case this is too far away, like a very long jump. And short jumps with these 8-bit CPUs have an offset maximum of plus 127 or minus 128. So it assumes that that you're going to exceed that. So it does a short jump in and a long jump away, and then the optimizer will see if it fits or not and gets rid of all that for you. So behind the scenes, it's doing all that work for you. And same with things like labels. Hopper, my assembler doesn't have labels like normal assemblers do. They have labels for jumps, and method names are labels as well. So goto being the root of all evil, I don't have labels. So I have break and continue in a loop. So this figures out that the label where that must jump to is the top of the loop, and if or break must jump out, and if not, it must jump to the top. So, and the same for like if else. You don't need to figure that out. You don't need to put labels for this. It just works. I've also been experimenting with optimization between the 65C02S, which is the Western design one, which is with the larger instruction set. And so, for example, the regular MOS 6502, which is what I have on this device here today. So this is an old, original 6502 with a smaller instruction set. And it is significant. The instruction set thing is significant. Let me show you. So if we look at the original MOS instruction set, that's the original MOS instruction set over here. Whereas the Western designs with the S, there's quite a few more instructions. And it increases the code density because a lot of these save you some space. So store Z is a good example. So what that does is it puts a 0 into whatever you want to target. And in the old 6502 assembler before they're both old, you used to have to load a 0 and then store it. So what I'm trying to do with the optimizer is make it so that if you write your code for one of them, it'll work. It'll do this behind the scenes for optimizing. So I do have examples of that. Maybe not in here. I think I do. I mean, all I need to do is look for an LDA 0. Yeah. So this loads a 0 into the accumulator and then stores it into all these 0-page values because it's clearing and it's initializing. So a very common thing to do. And for the S version, you just use STZ here. And behind the scenes, depending on which CPU you're targeting, the optimizer will do that too. And then the other one is these bit operations on the 0 page. So it takes 3 instructions, and so this bit operation on the 0 page is 2 bytes long. The instruction and the address on the 0 page. To do the same thing in regular code is 1, 2, 3, 4, 5, 6 bytes long. So it's 3 times as long. So behind the scenes, the optimizer will take these sorts of things and convert it into these. Anyway, that's what I've been up to. Building a toolchain for 6502 to have a 6502 assembler that's written in Hopper and making it work on these RetroShields. So I'll do a series of videos on this subject, first on the 6502 because that's what I've got the furthest with so far, and later on the Z80, which I've also been working on. So this will serve as the introductory video to that, and then I'll follow up with subjects on all the different parts of the toolchain and how to actually get this up and running on either a Mega or one of these Teensies, but I highly recommend the Teensy if you're going to do this. The Mega, I think, is the cheaper option, but it doesn't run, you can't run the 6502 at 100 than about 100, faster than about 100 kilohertz on the Mega, whereas on the Teensy you can run the 6502 at full clip, whatever its processor speed is, usually a megahertz, which is fine. I mean, we're not here for speed. If we were, we wouldn't be on these 8-bit machines, would we? We're here to just see how much we can do with them. Anyhow, I look forward to your feedback and your input on the subject. I'm keen to hear if anybody else wants to actually try and get this up and running. This definitely has been the most approachable and accessible platform for getting up and running on a 6502 of the ones I've tried and played with, because I've got a few other examples. I've got the 65 Arduino and I've got the Neo 6502. But in terms of getting this up and running at your place and getting playing on a 6502 or 6809, it also supports the S version. You just have to do a jumper on it. I'll do that demo as well. There'll be some links at the end of the video to more about Hopper, so that you can learn more about the language, and maybe a link to my original version that I had running on the 6502. So this is a rework. I'm doing like a version 2 of the 6502 runtime. And part of the reason is because my original was written directly in assembler, in Notepad, without the sort of advantages of a nice development environment and easy source navigation. Go to my definition, jump around, jump back, compile and look for errors, and jump to the errors. So if I have a you can see things happening at the bottom of the screen there. So if I have a syntax error in here, for example, I get the benefits. There's space in there, for example, F7. So at the bottom of the screen, I've got an error message and I can jump to it. So if I was somewhere else, for example, already, so I was in this file and I press F7 and it's error at the bottom of the screen. Let's just flip that. So what does it say? No local declaration assembly or something like that. And I can double click on that and it'll take me to the error. So just that simple convenience was quite a pain in the ass for most of the tool chains that I've seen out there for 6502. They're all sort of very command liney and as old as the processor in terms of the way they're expecting you to work. So I decided to build a modern environment to write 6502 assembler in, and one that's comfortable and saves you from yourself. As I said, no go-tos, no labels, but you've got if statements and loops and this kind of hierarchy, and really great and fun, very quick to, I've been porting from my old assembler, which is, legacy assembler. I've been porting into this version, and it's really quick to get things running. I mean, I think I've got a good example of that when I was trying to do my timer tick. I've got, right now this doesn't have reference types, and longs, 32-bit integers are reference types in Hopper because it's designed to run on 16-bit machines. So when you want to get the time in seconds, you're trying to get the time as a uint rather than as a, the millis convenience, the millis on the microcontrollers and on the on the peripheral chips for the 8-bit machines. They're basically longs. So to get from long millis to a uint seconds, I want to divide by 1,000. So the only long API I've currently implemented is long, divmod. And the way I implemented it is I just cut and pasted from my original version that I wrote just over a year ago. And so, all this comes from somewhere, and I always give credit in the source to the, where did I find these algorithms? And then, so this is what divmod, divmod, it combines div and mod into one. Basically the results, the L result is the mod and the L next is the div. When you divide one 32-bit number by another 32-bit number, you have a remainder and you have the result. So you can get both the mod and the div API out of this single function. And you can see it's not a very complicated thing to do, to divide, but it looks so much more clear when it's structured like this. You can understand what it's doing, like it's jumping out when it breaks here, and when it gets to that curly brace, it's going back to the beginning again. And the conditions, if carry is set, come into here. If not, go past. If 0 is set, break. If not, continue. Just a really nice way of doing assembler. Anyhow, if you're, I want to do a whole series on how to write more optimal assembler. So, you see my assembler and you say, well, shit, you wasted a whole bunch of space doing that. You could have done that in 3 lines. I'd like to get that sort of feedback. And I think the best place to do it is on my Discord server. just to make a channel on my Discord server and put up challenges there where I put out, you know, here's 10 assembler instructions in 6502 assembler to do the following. Show me how I've done it badly and could do it better. How would you optimize this? So I think that'd be a pretty fun interactive thing, is to interact on optimization, trying to do a better job than what I've already done, trying to make it more efficient. And again, the focus here is not on speed, the focus is on size, to try and see how much we can shoehorn into these little boxes for now. And then once we've got it shoehorned in the box, then we'll figure out how to make it fast. First we'll make it work, and we'll make it small, then we make it fast. All right. Thank you for watching, and if you are interested in engaging on this, send me a message and I'll send you an invite to the Discord server.